All right, so the method that we actually used in example 1 is called implicit differentiation. What does this mean? Well, first let's talk about the word explicit. If y is defined explicitly as a function of x, what do we mean? We mean we can solve for y. We can make y equal x stuff. We can solve for y. Y is equal to some x stuff. Whereas if y is defined implicitly as a function of x, we cannot solve for y, right? So in this example, notice we didn't solve for y first and then try to take the derivative. We just took the derivative of both sides, and then using chain rule, every time you take the derivative of y stuff, you hit it with a y prime, and we went ahead and solved for y prime, we solved for the derivative. And those are the steps of implicit differentiation. You are first taking the derivative of both sides with respect to x. When you do that, you're remembering chain rule. And then you're going to go ahead and solve for y prime. If you're watching other videos and reading the textbook, remember that y prime, an alternative notation for it, is dy dx. I encourage you to watch other videos online. If there's one step in the solving part that can be difficult for some people is if there are multiple y primes. If there are multiple y primes, you want to get all the y primes, get all the pinks on one side of the equation, and then factor them out. You will see some examples of me doing that later in this lesson. And one thing I just want to say is that I did make this video initially, and I did it too long, doing too many examples, and so I'm coming back and redoing it. So if the colors are a little different from the PDF that you have uploaded on the Google Drive, I apologize, but I do think that having it in video format is beneficial for quite a few students. All right, that said, example 1b. So we're going to use part A, the work that we did in the previous video, to find the instantaneous rate of change of y with respect to x. That's code for go find y prime, dy dx. And we're trying to find that instantaneous rate of change at a particular point when x is 3 and when y is minus 4. So in example 1a, we found that y prime was minus x divided by y. Plugging in 3 for x and minus 4 for y, we get that y prime is 3/4. Everywhere I see an x, I'm putting a 3. Everywhere I see a y, I'm putting a minus 4. An alternative notation for this is to write dy dx with a big vertical line that means evaluate that function y prime dy dx at a particular point, and then they write when x is 3 and when y is minus 4. Just wanted to point that out because you might be seeing that in other videos or other texts. Okay, so we have found the instantaneous rate of change of y with respect to x at this particular point. We have found, said another way, the slope of the tangent line to the curve x squared plus y squared is 25 at the point 3 minus 4. Now, because it is possible to solve for y, we can do this without implicit differentiation, but it's going to require a little bit more work. I do want to illustrate that, though, so that we see that we are, in fact, finding the correct slope. So let's do this problem again, but a different way. So first, let's go ahead and solve for y. X squared plus y squared is 25. Subtracting x squared from both sides gives me y squared is 25 minus x squared. Taking the square root of both sides gives me y is equal to plus or minus the square root of 25 minus x squared. Now, x squared plus y squared is 25. You may remember, and if you don't, that's okay, but that is the equation of a circle centered at the origin of radius 5. The positive square root, when y is positive, we're above the x-axis. And then the negative square root, we're below, when y is negative, we're below the x-axis. Oh, and I'm just noticing from my previous video, I used a different color. Boom. So here, if we break this up into two separate equations, y is the positive square root of 25 minus x squared. That's a function of x. The green alone passes the vertical line test. And y is the negative square root of 25 minus x squared. The lower half of that circle passes the vertical line test. It is a function of x all on its own. Then we can answer this question. Find the slope of the tangent line to this circle, x squared plus y squared is 25, at this particular point, 3 minus 4. But to do that, we need to understand that the point 3, negative 4 lies on the bottom half of this circle. And the question is, what the heck is this slope? Okay. But if we solve for y and recognize that we're on the bottom half of the circle, the bottom half of the circle, then we do not need implicit differentiation. We can go ahead and find y prime for the orange function as usual. Okay? Right, so oops, pick up some color. Since the point 3, negative 4 is on this bottom half, y is the negative square root of 25 minus x squared. If we take the derivative, then we can find the slope at that point. If we take the derivative, we can find the slope. At the point 3 minus 4. When x is 3, y is minus 4. All right, so let's do it. So y is minus the square root of 25 minus x squared. When I want to take this derivative, I first want to acknowledge that this is minus 1 times 25 minus x squared all to the 1/2 power. To get me set up to use my constant multiple rule and to get me set up to use my power with chain rule here. So I haven't taken a derivative yet. Here I go. Y prime is equal to the derivative of a constant times a function is the constant times the derivative of the function. When I feel free to go and do some scratch off to the side, but I'm going to jump in and do chain rule right away. When I look at this, I see one function of x, 25 minus x squared, composed with another function of x to the 1/2 power, square rooting. So I'm going to go ahead and use chain rule. The derivative of my outside function is just power rule, 1/2 stuff to the 1/2 minus 1 power. And that stuff right here is 25 minus x squared. So I've taken the derivative of the outside function, evaluated at the inside function, and now chain rule, I'm going to multiply by the derivative of the inside function. The derivative of 25 is 0, minus the derivative of x squared is going to be a minus 2x. What the heck is 1? 1 is 2 over 2. To subtract fractions, I need a common denominator. Let's go ahead and clean that up. It's all multiplication. We've got minus 1 times a half times minus 2. That's just 1. So y prime is x times 25 minus x squared to the to the minus 1/2 power. 1/2 minus 2/2 is minus 1/2. Okay. This is a times 1. Order doesn't matter in multiplication. Leading with the x is kind of nice. 1 minus 1/2. Sorry, 1 minus 1. I can't talk. 1/2 minus 1 is 1/2 minus 2/2, which is minus 1/2. And we are done, but let's go ahead and clean this up. We have y prime is equal to x times stuff to the minus 1/2 power is 1 all over that stuff to the 1/2 power. Multiply fraction straight across. We have x all over to the 1/2 power is notation for square root of 25 minus x squared. And we are good. So the value of this function is it tells me the slope of the tangent line at any point on the bottom half of the circle centered at the origin of radius 5. I specifically want the slope of the tangent line to the bottom half of the circle at the point 3 minus 4. So this happens when x is 3. I'm going to go ahead and plug in 3 for x, and then I will have my slope. Almost done here. Y prime is 3 all over square root of 25 minus 3 squared. Y prime is equal to 3 all over the square root of 25 minus 9, which is square root of 16, which is 3/4. Beautiful. We are happy we got the same result as we did with implicit differentiation. But notice how much simpler this was, because we didn't have to make that decision to realize we were on the bottom half of the circle. I encourage you to go ahead and click these Desmos links to look at all the slopes of those tangent lines here. And also for future classes in differential equations, we actually look at slope fields. This might be kind of fun to look at. It is optional. Thank you.